In this video, we want to talk about concurrency. Concurrency is a way of having parallel processes within our one process. Now, so far we have seen sequential code, meaning that one thing happened after the other, one operation happened after the other. In concurrent processes, we can have operations that happen in parallel, and also we can have communication between those operations. Okay, so when we look at a process, concurrency can be achieved by having multiple threads. Those threads have their own control flow. The problem is that Haskell 98 does not support it. The solution, of course, is concurrent Haskell, which is a language extension that is enabled by default. So we don't need to enable anything, but just be aware that this technically is not standard Haskell. Okay, so in concurrent Haskell, the process still looks like this blue ball, where we have multiple threads in them. Now, in a normal program written in C, for example, the threads you would create are kernel threads, meaning that those threads are scheduled by the operating system. In this case, this is not true. In concurrent Haskell, we have a runtime system that is then managed by itself, and the threads that are running in it are also managed by the system. So in the end, Haskell might only use 2 of your cores, so it has some, duo multi-threading, but it runs 1,000 threads within its runtime system. So the important question, of course, is how does communication work between it? Since we would need some kind of monad, don't we? Because there are side effects that happen with threads. Well, let's look at how to spawn threads first. You can import everything you need with import control.concurrent. In there is a function called fork.io. This one takes an IO action and simply executes it in a new thread. What it returns is an IO of the thread ID, so that can be used in order to identify the thread. So this is basically it. This is spawning a thread. Again, this is very important. It is spawning a thread within our runtime system, not within our operating system. But now the question is, how do those threads communicate? Is there any, shared memory? Are there return values? Since, as we've seen from the definition of fork.io, we don't have a return value for our thread. So how do we communicate with it? So the easiest example of communication with a thread is giving it some arguments. So in this case, we have a function fab, which adds A and B and then prints them to the screen, and as we can see here, we can fork on this function, of course, with the arguments supplied. So at least we know how to give the threads some arguments. But now the question is, how do we handle return values? And do we have something like shared memory? Well, we do. And this shared memory is called MVars. So that is a data type within Haskell that represents a mutable location that is shareable. So this means that this is some location in memory that can be shared between threads, where they can, put stuff into and then take some stuff out of it. The very important thing is that the actions on MVars are atomic. So this means that if 2 threads are trying to maybe put something into the MVar at the same time, then the runtime system should make sure, except for some exceptions, that the actions are atomic and there are no race conditions. Okay, so let's look at an example. Let's say we have 3 threads that all share one MVar. The important thing is that this data type is bidirectional. So a thread at any point in time could put something into it or take something out. Let's assume that thread 1 and thread 2 are trying to put some data into the MVar, and thread 3 tries to take something out of it. Well, let's assume that thread 1 goes first. And in that case, the data goes from thread 1 to the MVar. Now the thread 1 is satisfied. The action has finished. So now thread 1 can do whatever it wants to do. Let's assume that thread 2 goes next. Well, it can't, because the MVar is already filled with data. So now thread 2 is blocking. At that point in time, the runtime system has to find another thread that might execute something. And in this case, it is thread 3 that is now taking the data. It now is satisfied, and now thread 2 can have a go. Thread 2 puts its data into the MVar, and now all of the threads are satisfied and they can continue their control flow. So, what functions do we have in order to work with MVars? Well, we have new empty MVar and new MVar that create a new, MVar. It's either empty or already filled with some data. And then there are the atomic blocking functions, take MVar and put MVar. Take MVar, of course, takes the data out of it, and put MVar puts some data into it. So here's an example where we, in the main IO action, we create an MVar, then take this MVar as an argument for the thread. So now the thread has this MVar location, and then the main IO action is trying to take something from the MVar. Well, that's not possible, and this operation would be blocking, since we have created an empty MVar, so there is nothing in it. So this means that we are waiting for the thread to put something into it. And that's exactly what's happening, right? We add A plus B and then put it into the MVar. And in the end, we take that in the main IO action and then print the result. Great, right? Well, we have a problem here, and that is a big gotcha with MVars. You would assume in a normal program that the thread computed A plus B, and the main IO action then printed it. That is not what's happening here. Remember that Haskell is lazy, and it is still lazy even when working with MVars. So what happened here is that A plus B got translated into a thunk, and this thunk got stored in the MVar. The actual addition was then done by the main IO action when trying to show the result. So this is really important, and if you're not too sure about that, please watch the episode on strictness, where I talk about thunks, because this is a big problem. But we can fix it with this sequential function application where we force the evaluation of A plus B. This is very important if you want to offload some workload on a thread. You have to force its evaluation within the thread so that you can be sure that the thread actually executed the action you wanted. Okay, so there is another data type that we can use, which are called channels. Those channels in some way are also existent in the language Go, but okay. Maybe you know it, maybe you don't. Channels are shared FIFO queues, basically, which are unbounded. So this means that the queue can grow in size indefinitely. They are implemented with MVars, so they have all the properties of MVars. And let's look at an example how such a channel works. Well, again, let's assume that 3 threads are sharing one channel. Again, a channel is bidirectional. And again, we want thread 1 and thread 2 to send some data and thread 3 to take some data from the channel. Well, let's assume again that first thread 1 has a go, then thread 2, and then thread 3. Well, thread 1 is sending something to the channel and is satisfied, as well as thread 2. They can send as much data as they want, since again, a channel is unbounded. So there is no restriction on how much data is within the channel. And now, since thread 3 wants to take some data, it can get some data. Great. So now it is satisfied, and the data of thread 2 is now at the head of the queue. Again, this is a FIFO queue, meaning first in, first out. Since the blue data was the first data to come in, it was the first to come out. And yeah, if some thread now at a later point in time wants to read something from the channel, then it will get the green data. Okay, so let's look at the functions that we have for it. Of course, we can create a new channel, which then would be empty, and we can write into the channel and read from the channel. So those are the data types that we can work with right now, together with the fork.io function in order to do some multi-threading. Now we will look at an example. Okay, so we want to look at an example where we have some file called threads.hs, which does the following. Well, we have some main IO action that wants to spawn some threads, which we will do in a second. And what we want to spawn is this thread hello. Thread hello computes a greeting and then prints it to the screen. Get greeting takes the thread ID of the currently executing thread. So with my thread ID, you can get the thread ID of the currently executing thread. And then it builds a greeting from that. It will say hello from and then the thread ID. After that, we force the evaluation of the greeting and then we return it. So this is really important. Again, if you don't know what this operator is, please watch the episode on strictness and thunks. Okay, so, well, let's do that, right? Let's create a main IO action that does that, maybe with one thread at first. So we do it like this, where we use fork.io in order to fork thread hello, and then we return the empty tuple. Okay, so how do you compile that? Well, you of course use GHC. If you don't know how to invoke GHC, please watch the episode on compiling. But the important thing is that you need to use a flag called -threaded. And when we do that, we compile it. By the way, it would work without this flag. Maybe let's try that, right? It still works, yet then you don't have any multi-threading features, which of course is, well, not what we want. Okay, so let's look at this. Let's execute the program. And yes, it says hello. But the problem is that what we're doing right here is not multi-threaded, which is weird, right? Didn't we just make a thread and then let it execute stuff multi-threaded? No, we don't. Because with Haskell, you have to tell it that it should use more than one core on your computer, so more than one processing core. You do that with +RTS -n. And now you actually have multi-threading. Why does that work? Well, let's look at the options that we have. And here we see that we have a lot of options, and one of them is this one, -n, which tells the runtime system to use a specific number of processors. The default, and that's the important thing, is 1. So this means by default you only use one processor, so you don't have any multi-threading. If you don't supply it with any number of processors, it will infer it automatically. I guess that it will simply ask the operating system how many cores the CPU has. Okay, so let's test this again. And yeah, as we can see, it works. But hey, something went wrong here. Why didn't we have any output? Again. But now it works again. What is happening? Well, let's go back into the program. As we can see, we fork thread hello at this point. But that doesn't mean that it immediately gets executed. Maybe the next action that is executed is the return of main. And if that happens, the program exits. So now we need some kind of way for main to yield. We need a sort of, well, we need some waiting mechanism in order to, let main wait for the threads. So how do we do that? Well, we want to use a, special way of doing this so that we actually see channels and maybe even MVars in action. So what we want to do is we want to let the thread tell us when they're done. So we want, as a last action for the thread to do, we want it to signal its ending, basically. So we want to, or well, not ending, let's call it exiting. We want to let the thread signal to us that it is exiting, because then we could wait for those signals here, and well, we could yield our main for as long as not every thread has finished. So okay, the first thing that we want to do is we want to use 5 threads in this case, so that we actually have something to synchronize. What we also want to do is we want to create a channel, because what we want to do is we want to have basically a channel of end flags. So this channel, this FIFO queue, will then hold some data that will signal to us that the threads are finished. Of course, the channel at first is empty. What we want to do is we want to get 5 data points from this channel, and then we return. Why does that work? Well, if every channel puts in 1 data point, 1 data unit, if you like, then we know that if we read 5 of those data points, then we've read the end flag from every single thread. So maybe let's do the signaling first, because this channel, of course, needs to be supplied to the threads. So that's what we're going to do right now, where we want to put the end flags as an argument for thread hello. But now we have a problem, which is we have to decide what data type the channel should have, because of course channels have an internal data type. So what data type do we want to use? Well, in our case, we want to actually use the empty tuple. Since we don't need booleans or ints, we don't need any kind of information because we don't have a return value from the thread. If we would have some return value because we did some multiplication or addition or some other math, we could use a channel of ints, for example. But we don't really want to do that. We just want to have a flag that signals to us that something happened, so we can use the empty tuple. And actually what we also want to do here is the actual signaling, which we do by writing to the channel of the end flags and writing an empty tuple to it. Okay, so now we have to wait for the threads in order to synchronize something here. So how do we do that? Well, what we do is we use a function called mapm_. This function is a mapping function that maps some list to IO actions of the empty tuple. Why is that helpful? Well, it is helpful for working with side effects like we do right here. Because what we want to do is we want to wait for the side effect of the threads to signal their ending. And this side effect, this waiting for a side effect, can be done with this mapping. How? Well, let's look at it. Of course, in the function of the mapping, we get some x from this list here, but we can ignore it. We don't really need that. So now what do? Well, we read from the end flags. Now, of course, we know that the data that we get out of this is an empty tuple, so that's fine. And this reading is blocking for as long as we cannot read anything. So we are waiting until we have read 5 data points from this channel. And that is the important thing. Then we can return. Actually, we can delete this return statement because mapm_ does return an empty tuple anyways. Okay, so let's compile this and let's see if it works. Okay, at least it's compiling, so let's execute it. And of course, we want to have it multi-threaded. So yeah, it works. But this program has a huge flaw, and I want to demonstrate that. So let's import system.io, and right at the top of main, we want to add something, which is disabling something that was enabled before. So what we do is we disable buffering on standard out. Normally, you have buffering on standard out. This means that every time you want to write something to standard out, it is first kept in a buffer, and that buffer gets then flushed at some point in time. So now we disable that, meaning that when we write something to the terminal, it happens immediately. So let's see if that causes problems. Spoiler alert, it will. So let's compile it again. And let's call the program, of course, with multi-threading enabled. And now we see this. So now we can see that every thread is trying to write hello from thread ID and then their ID at the same time. And this causes problems. So as we can see, we can also run this a bit more often, and yeah, it gets really chaotic. I mean, here it's even weirder. This has actually never happened to me before, where one thread was actually able to write its message, but the other ones weren't. Okay, so let's look at where the problem is. Well, of course, the problem is within the printing. Let's look at the printing a bit more. Here, we never acquire a lock on the resource. So the resource in this case is standard out, since we are writing to standard out. And this resource is shared between all the threads, of course, because they can all write to the resource. Now, buffering made it possible for us to do this without acquiring any locks, since the buffer orders messages. But this is not always true for every resource. If you have a hardware resource, or if you want to talk to a server or something like that, then you have huge problems when not synchronizing when a thread can actually do something. Because the big problem is that the threads don't even know that other threads are waiting to, well, write something to standard out. So a huge race condition is happening here. Well, how do we fix this? So the fix was something that I've already hinted at. I was talking about having a lock for the resource. The resource in this case is standard output. So how do you make such a lock? Well, we will do it with an MVar. So what has changed from the last program? Thread hello now has an additional argument called mutex, because that's exactly what it is. If you don't know what a mutex is, I've linked to some information in the description of the video. So what we do is we have a mutex that by taking something from the MVar, because the MVar now is our mutex, we acquire a lock on standard out, then we print the greeting, and then we release the lock again. It's also very important that we do not acquire the lock before we have the greeting already pre-computed, because we don't have to wait until greetings are computed, right? The only resource that we are hesitant and careful about is standard out. Okay, so I've rewritten main a bit. So now we fork also with map m underscore. I'm using const with the function application here in order to have this sort of thing where we ignore the first argument. You can do that with const and then a function application. Okay, and so we spawn n threads. We supply it with a mutex and the n flags. We then put something into the MVar so that the mutex can now be acquired, and then we wait for the end flags. So the mutex is nothing but an empty MVar, right? So what's happening is that at first we have an empty MVar, we spawn the threads, they can already pre-compute their greetings if they like, then we put some data point, in this case it's just again an empty tuple, into the mutex, and now they can acquire and release the locks. So here it is acquiring the lock, and here it is releasing the lock. Again, the rest, so writing to the channel, for example, is atomic anyways, so we don't have to protect it with a lock. And again, computing the greeting is also something that does not need to be protected since we don't have a shared resource here. The only shared resource is standard out. So now we have forced synchronization between the threads. This program is also linked to in the description of this video if you want to take a look. I've already written some comments in it that should explain what's happening. But okay, so let's compile this and let's run this program. It should now, well, yes, it does. It prints from 10 different threads the thread ID. And as you can see, it now is perfectly synchronized. Synchronized in the sense that the shared resource, standard output, is protected by this mutex here. Okay, so those are the basics of concurrency. Yet, MVar and channels are actually not the preferred data type. And we will look at other data types to use with concurrency in another video. You wouldn't believe how many coffees I run through making one of these videos. If you'd like to support them, you can do so on Ko-fi, where you can, well, buy me a coffee. Any support is greatly appreciated. Thank you.